Hello, everyone, and welcome to the worksheet 15 video key. All right, so we are going to be talking about the SN1 reaction today. And the activity has us starting out classifying alkyl halides, again, as primary, secondary, or tertiary. So this one with the alpha carbon having one carbon attached is primary, secondary, primary, tertiary, secondary, and lastly, primary. So it says circle all the secondary and tertiary halides. So these substrates tend to react more readily under SN1 conditions. Cross out all the primary alkyl halides. These are too slow for a reaction. So I will just kind of add a little something extra here. I just want to put like, unless a simultaneous rearrangement with the loss of the leaving group forms a more stable carbocation. And I want to make that distinction just because like in these two cases, these would not undergo an SN1 reaction. Because recall that we do not form primary carbocations, they're too unstable, and there is no rearrangement in these cases that would lead to a stable carbocation. So we definitely cross those out. Right, but actually this one is sort of a tricky one, right? Because it looks like it's primary, definitely not going to occur, except for the fact that you can do a simultaneous methide shift with loss of the leaving group. Right, so this one, all right, can occur with methide shift. And loss of the leaving group simultaneous. So this one is kind of like a special exception to the rule. All right, moving on. The SN1 mechanism, right? So recall that this is what we call a stepwise mechanism that involves multiple steps. So the first step is loss of a leaving group, assuming that the leaving group is a good leaving group. And bromide is a good leaving group, so we can go ahead and have it leave. And we'll go ahead and write in, we did a loss of a leaving group. We form this carbocation intermediate, right? That is trigonal planar and bromide. And then the nucleophile, which is methanol, can come in and attack this from either side with equal probability. Right? So we can kind of have it come in and attack this way or this way. Right? And because it can attack from both sides, we can get both the retention of configuration product and the inversion of configuration product. And then lastly, the bromide or some more methanol actually can come in and do a proton transfer. Go ahead and draw that on both intermediates to get the product. So let's look at what we were actually asked to do here. Complete the mechanism above by filling in the curved arrows to depict electron flow. Is the methanol nucleophile involved in the rate determining step? Right, so no. Right. only the Rx substrate, which happens to be this chiral reactant, is involved in the RDS, the rate determining step. By the way, I want to finish labeling this. This one that I did in green. Okay, so it says the SN1 reaction is first order, which means that the rate is only dependent upon the concentration of one reactant. The reaction below shows a first order rate equation. What happens to the rate when the concentration of tert-butyl bromide is doubled and the concentration of methanol remains the same? Right, so it is doubled, right? Because this is the one that's involved and it's the substrate, right? So if we double that, double the rate. What happens when the concentration of methanol is doubled and the concentration of tert-butyl bromide remains the same? It would not change, right? It would remain the same. Then what happens to the concentration, to the rate when the concentrations of both methanol and tert-butyl bromide is doubled? So this would have no effect, right? But the tert-butyl bromide would double it. So it would double. Okay, so determine the hybridization and bond angle about the carbocation. So recall that the carbocation intermediate, right, which was any carbocation intermediate really, right? So we'll do, I guess I'll use the one from the example mechanism. Right, so that carbon is sp2 and trigonal planar. The carbocation intermediate A chiral, right? So we'll get no, it is not chiral because it does not have 4 different groups attached. So is the product chiral? Yes, the product is chiral. What is meant by plus En? Means plus the enantiomer, right? Which means that you would get both the product that was drawn and also the enantiomer. So you can just draw from your image. Or you could draw it the same way and just switch in 2 groups. Okay. Unlike an SN2 reaction, where the leaving group departs and the nucleophile approaches at the same time, the leaving group in an SN1 departs before the nucleophile approaches. In SN1, the mechanism shows the carbocation is formed in the rate determining step. The following are observed for the relative rates of SN1 reactions. Classify the alkyl halide as methyl, primary, secondary, or tertiary. Draw the structure of the carbocation intermediate. Okay, so this one is methyl, followed by primary, secondary, and tertiary. And carbocation be this one, We're basically just losing the leaving group to get the carbocation. Okay, and then I'm going to put a special box around those and just write 2 unstable do not work. Right, so even though it has a relative rate, these do not form, right? This is going to be a very, very slow reaction. In reality, you might get a little product, but not much at all. Nothing worth writing home about, right? Whereas secondary is sort of okay, right? We'll just kind of write this one is pretty slow. Probably get like a low yield of product. Whereas this one, woo, right? Fast. This one definitely forms quickly. This is a great substrate. Really the only good substrate of any of these in an SN1 reaction. So next, comment on why increased substitution pattern around the alkyl halide increases the rate of an SN1 reaction. Make the connection between substitution patterns and transition state energy of the SN1 reaction. So the first thing I want to state is that, right, when you have a carbocation, right, we'll just write more R groups means more hyperconjugation. Making it more stable. Okay, so increasing the substitution increases the amount of hyperconjugation, which increases the rate of the SN1 reaction. Because the carbocation is more stable, and therefore it can form faster. Right? So the second one is make the connection between substitution patterns and transition state energy. Right? So tertiary carbocations being more stable, i.e. lower energy, will have a lower activation energy for the rate determinant step. So basically, as the carbocation intermediate gets more stable, the activation energy is lower to get to that intermediate. Okay, so as mentioned, transition state energy. Tertiary carbocations being more stable, lower energy, will have a lower activation energy for the rate determinant step due to the lower transition state energy. So the reason for that is in the transition state, and I wish I had a good place to draw that, but basically let's use this space right here. What's happening in the transition state, right? We have R, carbon, R, R. And remember that the loss of the leaving group is what happens in the transition state, right? So this is already starting to take on some negative character, and the carbon starting to take on some positive character. So if you have a more stable carbocation, not only is the intermediate full carbocation more stable, but the transition state to get there is also more stable because it's starting to form even in the transition state, even though it's not fully formed. So this partial positive that's starting to form is more stable due to the R groups, right, stabilizing that carbocation. Okay. Hopefully that makes sense. Let's start talking about the factors that govern the rate of SN1 reactions. So first, the leaving group. The leaving group is super important, just like it was in SN2 reactions. The better the leaving group, which is the weaker bases are better leaving groups, the faster the reaction will go. And recall that the best leaving group is iodide, and that's because iodide is the weakest base out of any of these. Remember that you can always think about that as the reciprocal of the pKa of the conjugate acid, which would be HF, HCl, HBr, and HI. What about the nucleophile, right? The nucleophile is not in the rate determining step of an SN1 reaction. Is it in the rate determining step? The answer is no. Right? Only the substrate is in rate determining step. So how would the rate of an SN1 reaction change if the nucleophilicity is increased? So you're using a stronger nucleophile. Does it matter, right? No. So no change. Again, if the nucleophile is not involved in the rate determining step, then it doesn't matter at all towards the rate of the reaction. It doesn't matter the concentration, and it also doesn't matter the strength of the nucleophile. That's why you can use both strong or weak nucleophiles in an SN1 reaction. Okay, SN1 reactions dominate under polar protic solvents. Recall that's a difference from SN2, which were better under polar aprotic solvents. Increasing the polarity of the solvent will increase the rate of the reaction because the polar solvent will stabilize the dispersed charges on the transition state more than it will stabilize a neutral reactant, right? So it's not stabilizing this so much as is this stabilizing transition states and intermediate, lowering the energy pathway to get there. Label the delta positive and delta negative areas on the molecules of the transition state of the SN1 reaction below. Right, so recall that as this bond breaks, the bromide is partially on its way to being formed. Right, so it's not a full negative, but it's a partial negative. And the carbon starts to take on this partial positive character. For some reason, we lost the bromide here. This mechanism, let's go ahead and draw that back in. Find and list 4 examples of a protic solvent system. Okay, so water. And you could even make this like a different color, make it super. Of course, it really should be both sides in that case. But it just needs one in order to be considered protic. So any sort of alcohol would work. I don't know why I make that orange. Okay, and you could use this alcohol, go ahead and change it, make it alcohol, about methanol. And even something like ammonia. That has NH bonds. All it needs is one, right, to be considered protic, but this does have multiple. These are all great examples of for protic solvents. So great in SN1. All right. So each of the following proceeds by an SN1 pathway and will have anywhere between 2 and 5 steps. Draw the mechanism in each case. So first we ask ourselves, do we have a good leaving group? If the answer is left, yes, right, and we have a tertiary substrate, great. can immediately do loss of a leaving group, right? Because remember, we only need to concern ourselves with, are we forming something stable in this process, right? We are forming, not only are we forming a tertiary carbocation, but we're also forming some chloride, right? So if there's a great leaving group and it's a tertiary substrate, then it is good to undergo loss of a leaving group right away, right? We'll make a little note. The leaving group, tertiary substrate, right? Great for an SN1 reaction. Then we can get our nucleophile involved and draw that out with the lone pairs. So you can draw the nucleophilic attack. Remember, when you're drawing out mechanisms, I highly encourage you to draw in all lone pairs. It helps to draw your curved arrows properly. Attack. Your active product. We're writing. Okay. And the byproduct is the sodium ions and the chloride ions. So some NaCl is also formed, but that's often left off because it's a inorganic byproduct that we don't really care about, and it's going to be a waste product anyway. All right, so this would be an example of just 2 steps, right? The shortest mechanism you possibly can have. What is an example of a longer mechanism? So now I notice that this hydroxide is a bad leaving group, right? So if it's a bad leaving group, I have to come around and say, I'm going to add an acid. HI is an acid, right? So the acid is needed to convert the bad leaving group to a good leaving group. Okay, we do have a tertiary substrate, which is great. That means eventually, once I have a good leaving group, I'll be able to form a tertiary carbocation. So what we can do is convert this into a good leaving group. I'll go ahead and draw in HI. Then show those are my arrows. Remember, you always need 2 arrows to draw a proton transfer. Right now, we have a good leaving group. Yay. And as soon as we have a good leaving group, now we're good to show the loss of the leaving group step. That will generate a stable tertiary carbocation, and it will also generate some water. So now we're ready for the nucleophilic attack. So in this proton transfer step, I transferred the proton to the oxygen, and then I also formed some iodide. I didn't draw it in at the time, but I can go ahead and draw it in now because it's going to be important to show the last step, which is the nucleophilic attack. Right, so here would be an example of a 3 steps. Right, so this one had a loss of a leaving group followed by nucleophilic attack. This one needed a proton transfer first because we had a bad leaving group. But now this is, once the nucleophilic attack occurs, this is neutral, so it's stable, so we don't have to do anything. In both cases, we formed a tertiary carbocation, so we didn't really need to worry about rearrangements. Those are already really stable. Let's go ahead and do another mechanism here Notice that the leaving group and the incoming nucleophile are not on the same carbon, and that the carbon backbone has changed. So this one is clearly going to involve a rearrangement, right? We will do a rearrangement. Right? Because the carbon backbone has changed. That is what is unique. Okay, so where should we start? Remember, we have to look at it and say, okay, what is the substrate? What is the leaving group, right? So bromide is a good leaving group. That's good. But this is a secondary substrate. That's not as good as tertiary. However, if we heat it, it can work in an SN1 reaction. And with a good leaving group, we can go ahead and show it leaving. Right in, loss of a okay, so we did loss of a leaving group. Now we notice that there's two methyls over here where there was only one before. So now is the time to think about a rearrangement. Okay, so we can do a methide shift. Secondary carbocation. Okay, we are going to form, after the shift, a tertiary carbocation. So that will definitely be more stable. Label this as a rearrangement. More specifically, a methide, a 1,2 methide shift. Okay, now, right, that we have the right carbon framework, we need to get the nucleophile involved. Really, methanol is the nucleophile. We need to go ahead and draw that in. So we can do our nucleophilic attack. Sure to draw exactly what is formed, right? This methanol had 2 bonds before. Now it's going to have 3 bonds and a positive charge. This is not neutral yet, so we are not done. We need to do a final proton transfer. And we can actually draw in another methanol, because remember, it's their solvent amount. This is a solvolysis reaction. There's plenty of methanol around. Draw in another one, do our final proton transfer. And then a little note that we'll also get as a byproduct some protonated methanol. That's okay. Okay. Next, asked to draw in the product of the reaction. So predict if the following SN1 reaction would undergo rearrangement. Be careful to indicate stereochemistry whenever necessary. Okay, so I guess we'll just make a first prediction, right? So do a little column, rearrangement. Okay, and then we'll just do like yes or no. Then we'll go ahead and draw in product. For products, depending on stereochemistry. Okay, so when we have loss of a leaving group, we're going to get a tertiary carbocation. So that cannot rearrange, more stable in this case, so no rearrangement. here, when we have loss of a leaving group, we're going to get a secondary carbocation. There can be a hydride shift to form a more stable carbocation. So the answer is yes, right? So we will end up with a tertiary carbocation. So once this leaves, there's a rearrangement, a hydride shift, right? So we'll write yes, hydride shift in this form. Okay, and because this is no longer a chiral center, then we don't need to write a dash or a wedge. So here we'll have loss of a leaving group. This will be a tertiary carbocation, right? So we do not need about rearrangement. Here we have a chloride leaving group. It's going to be secondary, and if we do a hydride shift, it can become secondary and benzylic. So yes, this one will have again another hydride shift, right? To benzylic, which means resonance stabilized. So what form? So form this one. Okay. Moving on to thinking about this one. Well, that this is a bad leaving group, but if it gets protonated with the acid, then it can become a good leaving group. So recall that it cannot leave to form a primary carbocation, but you can have a simultaneous hydride shift and loss of a leaving group, right? So essentially, once this becomes protonated, you can do simultaneous loss of a leaving group and methide shift, right? So, yes, we get a methide shift, right? It will happen at the same time. That's really important, right? Simultaneous with loss of a leaving. So we will end up with stable tertiary carbocation. All right, and then here, loss of this bromide leaving group, that will give us a secondary carbocation. And can we do a hydride shift? Yes, we can. And if we do, it will become a tertiary carbocation. Okay, so yes, we are going to have a hydride shift. This one specifically will be the one that migrates right on over, and we'll end up with in its Fisher projection. Okay, so let's go ahead then and draw in the product. So by the way, this is not a chiral center. I know you see a dash and a wedge. That's okay. It's not a chiral center. Right? With no rearrangement, our nucleophile will end up attached right at that carbon. And because it's not a chiral center, we don't need to draw a dash or a wedge in the product. And we certainly don't need to draw enantiomers if there's no chiral center. So we can go ahead and draw in. The hydrogen gets lost through proton transfer. Right? We'll just make a little note, not a chiral center. Okay. Right? And no chiral center either. So we said we were going to get a shift, right, from the secondary carbocation to a tertiary carbocation. Again, methanol is our nucleophile. Right? We actually get the same product as we did up above. So two different substrates ending up giving us the same product. No rearrangement on this third example. So that means that the OH group that comes from the water, remember one of the hydrogens will be removed through proton transfer, will end up right at that same carbon that lost the leaving group. Okay, this one definitely shifted, went from secondary to secondary and benzylic. So the nucleophile will come in here. This is going to form a chiral center. So we can go ahead and indicate that by either drawing both enantiomers or at least drawing one of the enantiomers and then writing plus En. Right, so you could choose to draw in one of those. Acetate group like this. Make a little note of this is acetic acid. So once we lose the proton, the rest of it is the nucleophile and gets incorporated. So write plus the enantiomer as well. So this one did shift because we cannot form primary carbocation. So we did a simultaneous methide shift to form a tertiary carbocation. And it will get attacked by the nucleophile, which is bromine. You're not forming a chiral center, so no need to indicate any dash or wedge. We did get a shift here because it went from a secondary carbocation to a tertiary carbocation through a hydride shift. Ethanol will eventually attack here. We'll lose the hydrogen through proton transfer. And we are going to get a racemic mixture at this carbon. By the way, now that this is not a chiral center, we don't really need to draw it as a chiral center anymore. So now we would actually have an ethyl group of methyl, and ethoxy group. So now that we have two ethyl groups, technically, right, we don't need, it's not a chiral center. So we can either draw it in kind of like it looks, right, not as a chiral center. Or we can draw it in as it simplifies to two ethyl groups, an ethoxy group, and a methyl group. Okay, propose a synthesis of the following target by indicating the necessary organic or inorganic reagents. Okay, so we remember whenever we start with a alkane, you always have to do the same reaction. You have no choice. You have to do a radical halogenation. And no matter where you want the bromine, it's going to go at the most substituted carbon. So that's something to note, right? We're going to do the radical halogenation reaction. The bromine will go on the most substituted carbon. Now this is a tertiary substrate and great for an SN1 reaction. We just need to look at what nucleophile we want and go ahead and add that. So this is a great leaving group, so no need for an acid. We can just go ahead and add in our nucleophile, which is phenol. Right, so this is our SN1 step. Okay, last page. Identify the reagents you would use to achieve the following transformation. Indicate if the reaction follows SN1 or SN2 pathway. Notice that we have a tertiary substrate. Right? With a tertiary substrate, it has to be SN1. Don't write SN2 for tertiary. Okay, so knowing that we can include the nucleophile. And typically weaker nucleophiles are used, so we'll go ahead and just make that an because we can just do solvolysis that as opposed to the sodium alkoxide. Okay, this is a primary substrate, right? And primary substrates are likely going to undergo SN2. They don't really work well at all in SN1 reactions, too slow. So because of that, we'll need a strong nucleophile, right? So this should be looking at the stereochemistry here, we have inversion. Inversion tells me that this should go SN2. And SN2, we need a strong nucleophile. So we'll write NaSH. Again, we're just going to leave out the solvent. We know SN2 reactions prefer polar aprotic and SN1 reactions prefer polar protic, but that doesn't mean we have to include solvent with every reaction. So a lot of times, many reactions can be done in many different solvents and still be successful. Okay, again, we are looking at inversion. Inversion is a dead giveaway that it is going to go SN2. If it's going to go SN2, I need a strong nucleophile. Sure that this is sodium alkoxide. Here we have a primary substrate. Here was tertiary, primary substrate here. Primary SN2. So we need to figure out what was our nucleophile, right? This carbon is the substrate. So this is the part that I need. So I can just use carbon. And next, we have a tertiary. Because it's tertiary, you know it's going to be SN1. SN1 typically uses a weaker nucleophile, so we don't write O- or ONA, we'll just write OH. All right, that is the end of the activity. You guys have a good